Hello everyone, and welcome to Energy Bar Graphs, qualitative examples. Qualitative means that we're not going to use complete numbers. We're not actually going to calculate amounts of energy. But we are going to use a new way of modeling the law of conservation of energy. We are going to use energy bar graphs. Here's an initial bar graph, here's a final bar graph, and then something in the middle we'll talk about called an energy flow diagram. So, in our first example, it's one that we've talked about a bit before. A ball rolls down the hill. Now, I've kind of written things a little differently here for you to look at. You notice that VI is 0, so it starts from rest, and it's above 0 height, of course. It's at the top of the hill. At the bottom of the hill, the height is 0, and VF is greater than 0. Now it's moving. Our system will include the ball, the hill, and the earth. So there's our system. And you notice I reach all the way down into the earth. Okay? And friction, this time I'm going to say yes. When we did this earlier with pie charts, we said no. So let's do one here where we will have some friction. Now, is this an isolated system? Well, the forces that would act on the ball would be gravity between the ball and the earth. That's inside. Normal between the ball and the hill. That's inside. And friction between the ball and the hill, and that's inside. No other forces. So all of the forces are internal. So this is an isolated system, and therefore the law of conservation of energy applies, and energy is conserved. So that means however much energy we have initially, we have the exact same amount of energy finally. Now we're going to get a little more numerical here. We're going to actually count boxes, as you're going to see. So let's start out with our initial energy bar graph. Initially, there is no EK, because it starts from rest. There is EG, because it's above 0. I'm going to say it has 4 boxes of EG. Now, again, how much is that really? I don't know. We're just going to call it 4 boxes. All right, so a little more numerical, but still not actually calculating things. And there's no elastic potential energy, because after all, there's no springs or rubber bands or other things. Now, in our energy flow diagram, this circle represents the system boundary. Here's what's in the system: the ball, the hill, the earth. And then that's it, because in this case energy is conserved. There is no energy flowing into or out of the system. This is where we're going to show that in later examples. Okay? So nothing flowing in or out. And then our final, at the bottom of the hill, there's no more EG, there's no EE, there will be some EDIS, and there will be some EK. Now, how much of each? It depends. I'm going to assume here there's about 1 box of EDIS, and therefore there must be 3 boxes of EK. Now why? Well, because energy is conserved. So if I drew 4 boxes here, I must draw 4 boxes over here, even though 3 are EK and 1 are EDIS. So notice we're still keeping track of all the energy here. Right? We've got 4 boxes initially, nothing flowing in or out, and 4 boxes finally. By the way, you'll hear me call these this later on, or in class perhaps. These are sometimes known as LOL diagrams. See, look, LOL. Oh, funny physics. Our second example is going to be a little different than ones that we've done in the past. Here we have a spring, and the spring is just sitting there. It's not stretched at all. And then I'm going to pull on the spring and stretch it with an applied force. Okay? So no stretch at all, stretch spring. Our system will be the spring, the wall, and the earth. So there's our system. Now, is this an isolated system? And for the first time, the answer is no. Right? Why not? Because me, the guy that's applying the force, is not part of the system. You can see it here in the picture. The applied force pierces the system boundary. Right? It goes through the system boundary. So there is an outside force being applied. Now, you might say, but wait a minute, why don't we just put, comma me here in the system and have me in there? Well, because if we're going to do that, then we need to put an E-me column in the initial and final bar graphs. And then we'd also need to be able to eventually calculate how much the energy changes in me when I stretch the spring. And, I'm a fairly complicated guy. And so that would not be the simplest thing for us to calculate. So instead, we'll leave me outside of the system and see what I end up doing to the total energy. So initially, there's no kinetic because it's not moving. There's no gravitational potential. We'll just call this height 0. And there's no elastic because it's not stretched. So initially, there's no energy. Finally, it's not moving. I just stretched it and I'm holding it. So there's no EK, no EG, same level, but there is some EE. Right? Oops. There is some EE, and I'm going to assume an ideal spring here. Right? So no E dis. So that means initially our pie chart would be a dot. There is no filling. Right? There's no energy. But finally, it would be all elastic potential energy. So nothing initially. I'm going to call it 4 bars of elastic potential energy. Again, I'm assuming an ideal spring so that it doesn't dissipate when you stretch it. So this is the first time we've seen energy not be conserved. And we're going to show that there's energy flowing into this system with our energy flow diagram. So first, a circle to represent the system boundary, a quick little picture of what's in the system, and notice I'm not in the system. But what am I doing? I am adding 4 boxes of energy into the system. So here's how we're going to show that. You'll like this. It's very graphic. See that big fat arrow? That big fat arrow is pointing into the system. See, it pierces the system boundary. And it is 1, 2, 3, 4 boxes long. I don't want you just to draw a regular old arrow. I want you to show the energy flowing in. Okay? And so here we have no energy. I add 4 boxes of energy, so we have 4 boxes of energy finally. Now, this process of adding energy into or taking it out of a system by means of an external force has a name. It's called work. And it is denoted by a capital W. So we are going to define work as the first energy transfer mechanism. Okay? This is how we move energy in and out of a system mechanically. The transfer of energy into or out of a system, and we use external forces. So if there are no external forces, like every example we've done before this, then there's no work being done. We don't show the big arrow here. If there is an external force, or more than one, they do work, and then we show that energy being added or alternately taken out. If it's taken out, we just draw the arrow the other direction, right? And then there's work being done. So this arrow will be a positive amount of work, because we're increasing the energy into the system. Right? Positive work is increasing the energy. Negative work would be decreasing the energy. Okay? So it's not a vector. Okay? It's a scalar. But positive and negative means whether you're adding energy or taking energy out. So here's a new concept, work. All right? And the energy flow diagram and the bar graphs around it are really good to kind of show that, so we can visualize it. No energy. We add 4 boxes of work. We end up with 4 boxes at the end. Let's do another one like this one. Here's our last example for today. So this guy up here has got a rope over a pulley. By the way, I'm going to assume it's a frictionless perfect pulley. And the box is up here. It's moving. It's above the ground. And he lowers it. At the end, he's just holding it. So it's not moving, but it's still a little bit above the ground. Right? System, box, pulley, earth. There's our system. You can also say the string if you consider the string to have, or the rope to have mass. But notice, I'm not in the system. Why? Because if we put me in the system, we'd have to have a way of keeping track of the energy changes going on within me, and that would not be easy. So instead, we'll leave me outside the system and try to look at what do I do to the total energy. So initially, it's moving, so there's some EK. Right? System's not isolated, sorry. So initially there's some EK. I'm going to assume it's not moving very fast, so I'm just going to give it 1 box. Again, we don't really know till we get math models and can calculate. It's really high up in the air, so I'm going to give it 4 boxes of EG. And there's no EE because this isn't a bungee cord, it's just a rope. Finally, okay, it's down here. Right? It's not moving, so there's no EK. It's much lower. So I'm going to give it 1 box of EG. If you actually take a ruler and measure this, this is a quarter of the way it was here. So I'm calling it EG. 1 box. No EE. And I said it was an ideal system, so no E dis. So look at what we have. We have 5 boxes of energy initially and only 1 box finally. What happened to that energy? Well, it flowed out of the system. So there's our system boundary. There is what's in our system. Notice, I'm not in there. And now we're going to have negative work done. energy flowing out of the system. So my arrow is pointing out. And in this case, it's 4 boxes long. By the way, 4 is not a magic number. It won't always be 4 boxes of work. It depends how you write it here. If I had written this as 3 boxes of EG, so I started with 4 and ended with 1, this would only be 3 boxes long. And this is called negative work because it's leaving the system. And by the way, it doesn't matter where you draw this arrow. You can draw it anywhere you want on the diagram, okay? It's just whether it's pointing in or coming out and how many boxes it has. So here we go again with another one where we're still keeping track of the energy, but it's a little more complex now, all right? And we're still just counting boxes. So I hope this helps you understand how we can use these bar graphs to organize our energy and this new concept of transferring energy in or out of a system by means of work using external forces. Hope you enjoyed the presentation.